Hi friends, Dr. Borole is here. Welcome back. Let us continue the study of instruments. Today we are going to study the first instrument, that is auto transformer. As the name indicates, it is the transformer. Whereas we have seen in the transformer, normally the output voltage is fixed. Means it have fixed input and fixed output voltage at various different current capacities. Whereas auto transformer is a transformer in which the output voltage can be made variable. For that purpose, the mechanical wiper arrangement is provided, by which we can able to change the number of output winding turn, so that output voltage will be proportional to the number of turns of the secondary winding. There are two types of auto transformers. Depending on the number of phases of the input supply, they can be either single phase auto transformer or three phase auto transformer. Three phase auto transformers are normally used in industry for speed control of AC motors. Whereas in our domestic use, normally single phase transformers, auto transformers are commonly used. There are two subtypes of auto transformer: the step down auto transformers and step up auto transformer. The step down auto transformer, the name itself indicate that the output voltage of these transformers are always less than the input voltage. Means it can provide us the output voltage from 0 to maximum up to supply voltage. Whereas the step up auto transformers are the transformer in which the output voltage is always greater than the supply voltage. Let us see the construction of auto transformer. Here in the figure, you will see a toroidal core in the form of a cylinder on which the winding is wound. The two ends of the winding, called fixed terminals, where the AC supply is connected. Whereas the output terminal, called variable terminal, is connected to this winding via a mechanical wiper. This wiper makes the electrical connection between the point of contact and the output terminal. And therefore, by changing the wiper position, we can change the voltage between either of the fixed terminal with respect to a variable terminal. The laminated core is normally used to reduce the eddy current produced in the transformer, which is as usual and similar to a fixed transformers. The equivalent circuit is shown here. The symbol of the auto transform consists of a single coil with two fixed terminals and a variable terminal which is moving on a fixed coil. The AC mains input is applied between the two fixed terminal and output is taken between the variable terminal and one of the fixed terminal. By moving the wiper on the winding, we can change the lower winding number of turns, and therefore the voltage developed between the variable terminal and lower fixed terminal can be changed. And that is also applicable to upper winding with fixed terminal, which is the top fixed terminal. It is similar to a variable resistance arrangement. A typical construction in 3D is shown here. The cover is removed and you will see there is a cylindrical coil on which the cylindrical core on which the winding is wound, and there is a wiper connected, and to the wiper there is a rolling type of carbon brush provided, whereas this winding, the area which is coming under the brush is de-insulated, means the insulation of the winding will be removed so that the carbon brush can make the contact with the winding. Depending on the position of the carbon brush, the number of turns with respect to the reference fixed terminal can be changed. For that purpose, the mechanical knob arrangement is shown. Also, there is a calibrated dial shown here, which is marked in terms of the voltage. So, when we change the knob position by few degrees, the output voltage between the variable terminal and the fixed reference terminal is proportionately changed. In case of three-phase thermostat or auto transformer, you will see there are three single phase auto transformers connected with the common shaft, and the three variable terminal with a reference, common reference is available at the output. So by changing the wiper here, we can change the three output voltage of the three auto transformer. Those are three phases. Let us see the auto transformer as a step down transformer. Normally, the winding fixed terminals A and B, the input voltage V1 is applied, which is having say N1 number of turns. This winding is also called as high voltage winding or HV winding. Whereas the number of turns between the wiper contact position and the reference terminal B is denoted as N2. And across N2, the output voltage is taken and load is connected. Now in this configuration, the load voltage is given by V2 is equal to N2 by N1 into V1, where N2 by N1 is called as transformer turns ratio. From this equation, we can say that the ratio of V2 by V1 is same as N2 by N1. And in this case, since the wiper is variable, which is moving on the winding, the N2 number of turns are adjustable. And therefore, obviously from this equation, if N2 changes, V2 changes. When N2 is 0, output voltage V2 is 0. If N2 is maximum equal to N1, then output voltage V2 is same as input. And in this case, the ratio N2 by N1 is always less than 1. And therefore, V2 is always less than V1. Now let us see the auto transformer as step up transformer. In this diagram, the same transformer is now connected with a single phase supply connected to the LV winding, low voltage winding, means between wiper and the reference terminal B, the input supply is connected and the output is taken across the fixed terminal A and B. The total number of turns denoted here is say N2, that is total secondary number of turns, and the primary number of turns are denoted by N1, that is the number of turns present between point C, that is the variable pointer position, and the fixed terminal B. Load is connected across the fixed terminal A and B, that is across high voltage winding or HV winding. Again, as per the transformer theory, the turns ratio is N2 by N1, that is equal to V2 by V1. And therefore, load voltage V2 is given by N2 by N1 into V1. Here we will see that N2 is always greater than N1 and therefore V2 is always greater than V1. And that's why since V2 is greater than V1, we are calling this type of connection as step up connection of the auto transformer. The same auto transformer can be connected as step down transformer or step up transformer. And this can be achieved by interchanging LV and HV windings. A typical application of auto transformer as a light dimmer is shown in the figure. It is also called as dimmer stat. So here you will see the auto transformer is connected in step down configuration and the output coming from the transformer wiper with respect to terminal B, that is the reference terminal, the load is connected and the load here is multiple lamps. Here three lamps are shown, but you can continue it with n number of lamps. The output voltage we know V2 is N2 by N1 into V1. So by changing the wiper, we can change the number of turns N2 and thus we will change the value of V2. V2 can be changed from 0 volt when wiper is at the bottom position to N2 is maximum equal to N1, that is V2 will be maximum, that is equal to AC supply voltage. And due to that, the load voltage is varied from 0 to maximum of the input supply voltage. And as the voltage across the lamps increased, the light intensity of the lamp will be increased. So when light intensity required to be reduced, we will reduce the voltage output from the dimmerstat. When it will be 0, there will be total dark. When we slowly go on increasing, the light intensity is increasing. One of the application of light dimmer or dimmerstat is in cinema theaters. We have seen where before starting of the movie, they will reduce the light intensity of the background lights to 0 and then the movie will be started. That's all about the auto transformer. It is a very simple instrument. Normally for testing purpose in the lab, when variable power supply AC power supply is required, then auto transformer or step down or step up auto transformer can be used. The next set of instrument is analog DC ammeters and voltmeters. These are mostly a PMMC instruments. They are having a analog pointer. They can be in different shape. Here, a sample square shape voltmeter and ammeter is shown. But the shape will be normally either round shape or square shape, or it depends on the requirement. They can be manufactured as per the requirement also. The dial will be marked in terms of voltage. The lower position is shown 0 volt and higher position will decide the maximum range of that particular voltmeter. Same is the case with ammeter. They are available with different physical sizes also. Whereas in this meter, you will see a screw position here shown by the red dotted arrows, that is called as zero adjust. Many a times when ammeter or voltmeter is not connected anywhere in the circuit, still they are showing some reading. This is basically a mechanical misalignment. So before using it in the circuit, and for the accurate measurement of the reading, we have to adjust the zero of the meter when 0 volt is applied. And for that purpose, this mechanical arrangement is provided called zero adjustment. A typical connection diagram of ammeter. We know the ammeter is always connected in series with the load, so that the current should flow through the ammeter and the same current should flow through the load resistance. So here ammeter will read the load current. Ammeter is always connected in series. And as we know that ammeter have very low input resistance between positive and negative terminal. Ideally speaking, ammeter have zero internal resistance. And therefore, while inserting the ammeter in series doesn't affect the current actually flowing through the circuit. And that's why ammeter is always inserted in series to measure the load current. Connection diagram for voltmeter now. Voltmeter have very high input impedance between its terminals. And voltmeter is always connected across the points across which the voltage is to be measured. Here we want to measure the voltage across the load resistance, which is say across the point A and B, and therefore voltmeter is connected across point A and B. Terminal polarity should be appropriately connected. Positive polarity of the voltmeter should be connected to the positive point and negative terminal should be connected to the negative point. If you reverse connect the voltmeter, it will show reverse deflection. And normally this reverse deflection will be mechanically stopped by the stopper. If it is a galvanometer type of instrument, then it also shows the negative voltage because the zero position is at the center of the scale in galvanometer, what you have studied in 12th science. All these voltmeters and ammeters of analog nature, those are mostly a PMMC instrument. What is PMMC instrument? It is called as permanent magnet moving coil instrument. Here typical construction of permanent magnet moving coil instrument is shown. It consists of a horseshoe permanent magnet shown here, and in this permanent magnet there is a gap. In this gap, a coil of a copper wire is suspended. This coil is pivoted coil and this coil is mechanically moving around the axis. The pointer is connected to this moving coil. That's why the name moving coil instrument. The pointer is pointing on a calibrated scale so that the deflection can be measured in terms of either voltage or current. Various parts of PMMC instruments as depicted in the figure are the permanent magnet, the soft iron cylinder for damping the movement. You will see here the coil is moving around a soft iron cylinder. When this soft iron cylinder is there, it will provide the easy path for magnetic flux and therefore and also provide the support for the moving coil. It will probably damping the rapid variations in change in the current flowing through the coil. Pivot is normally a mechanical bearing type of terminal which is freely moving. Pointer, scale and mirror are the additional three parts which can show the reading. Typical construction shown here. See, here the mechanical bearings called jewel bearing are shown. The pointer is connected to this movable shaft. To this shaft, the coil is connected, which is shown here by the square shape. The hatch portion is a fixed soft iron core, whereas the horseshoe magnet north and south poles are shown. Whereas there is a control spring provided which will restore the pointer always to zero position. Now the working principle, the 3D view of this construction is also shown here. The working principle of the PMMC instrument is as shown below. When the current carrying coil placed in the uniform magnetic field, it experiences the force. And this force is proportional to the flux density in the air gap, the current flowing through the coil, and the length of the conductor of the coil. Here, when the current is flowing through the coil, it experiences the force. And due to this force, the coil deflects. When the coil deflects, the pointer is getting deflected on the scale. And from this expression, F is equal to BIL, we will see here the force of deflection is proportional to I. And therefore, when the current to be measured is passed through the coil, the proportional deflection will be produced on the scale. Flux density B and the length of the coil is fixed because once the instrument is designed, these two parameters are the physical parameter and therefore from this equation we can understood that the deflection force F is proportional to I. How this PMMC instrument can be used as a DC voltmeter, DC ammeter. Now in this case, as we know, the ammeter is always connected in series. Normally, to make PMMC movement as ammeter, a shunt resistance RSH is connected across the PMMC instrument. And then this total PMMC instrument with the shunt is connected in series. So we will see that the current I, that is the load current or current to be measured, which will be divided in two parts. One is going through a PMMC instrument and another is going through the shunt because this forms a parallel combination. PMMC instruments are normally carrying very low currents and majority of the current is passing through the shunt resistance. Whereas the part which is flowing through the PMMC instrument is proportional to the load current. We will shortly derive the relationship how much I, the load current or current under measurement and current through PMMC instrument IM is related. So from this figure, we can see Im is equal to, this current Im is equal to, let us apply the current division principle. Im is equal to total current I into RSH upon Rm plus RSH. So current which is flowing through the meter can be obtained by taking the resistance which is parallel to the instrument divided by the total resistance of the instrument as well as shunt. This is the current division principle. From this equation, if we take I on the left hand side, then we can say that I is equal to Im into bracket 1 plus Rm by RSH. Just reshuffling of the equation. Whereas 1 plus Rm by RSH is constant. Let us replace it by K. And therefore, I is K into Im. Whereas the dial of the instrument shown here is calibrated in terms of the actual current measured to compensate the value of K. A typical dial shown here. This is 0 position and the 10 ampere maximum position shown for this meter. A typical dial for voltmeter is also shown here. The second dial indicates the dual type of instrument which can capable of measuring voltage as well as current. So two scales are provided. The meter should be appropriately connected either in series or in shunt to be used as voltmeter or ammeter. From the expression of I we have derived the voltage across the resistance Rm and RSH is Vm. Let us see the voltage across RSH and the PMMC instrument resistance Rm, that is the parallel combination, and voltage is denoted by Vm across it. But Vm is Im into Rm and that is same as ISH into RSH. Whereas what is ISH? ISH nothing but from this circuit, ISH is nothing but I minus Im. That is substitute here. And therefore, from this equation, if you take RSH on left hand side and remaining term on right hand side, you are getting the expression RSH equal to Im into Rm divided by I minus Im. All the right hand side parameters are known, so that from this expression you can calculate the effective shunt resistance required for the given measurement range of current and the selected PMMC instrument, where Im is the full scale deflection current of the PMMC instrument. You can extend the range of these ammeter by changing the value of RSH. So from above expression, we know I is equal to 1 plus Rm by RSH into Im. That is K into Im. So therefore, from this equation, I1 is equal to, say for example, first full scale current is equal to 1 plus Rm by RSH1 into Im. That is K1 into Im. For second range, we use the resistance RSH2. For third range, we will have a resistance of RSH3 and they are connected like this via a switch. So now your instrument, PMMC instrument is working as a multi-range ammeter. For example, first range is for 10 ampere, second range is for 20 ampere, third range is for maximum 30 ampere. Depending on value of RSH1, RSH2 and RSH3, you can decide the maximum operating range of the ammeter. And here the switch, multi output position switch or multi-pole switch, can be used for changing the range of the ammeter. Here, this is optional thing. Basically, it is the derivation of current division principle. And from the circuit, we know I is equal to Im plus ISH. Since voltage across Rm and ISH is same, that is Vm, therefore I is equal to Vm by Rm plus Vm by RSH. Take Vm common and you will get in the bracket 1 by Rm plus 1 by RSH. Therefore, I is coming out to be Vm. Now parallel combination of this 1 by Rm plus 1 by RSH comes out to be Rm plus RSH upon Rm RSH. See here Vm by Rm shown in the blue color, that is nothing but Vm by Rm is equal to Im. And therefore I is equal to Im into 1 plus Rm by RSH, that is K into Im. This formula we have directly used as a current division principle. Now PMMC instrument can be used as a voltmeter as shown or as discussed below. The PMMC instrument to be used as voltmeter, normally a high value of series resistance connected in series with the PMMC instrument. For example, there is a circuit with a DC supply, say VDC, the resistance R and the resistance RL. And we want to measure the voltage across RL, that is voltage V we want to measure. So we will connect a voltmeter made up of PMMC instrument with a series resistance is connected as shown. The dotted box indicate the voltmeter configuration using PMMC instrument. Now in this instrument we can see the voltage drop across the meter, that is across the meter resistance Rm, is denoted by Vm, and voltage drop across the resistance Rs is denoted by VRS. And from this figure, using Kirchhoff's voltage law, we can easily find the total voltage V is equal to Vm plus VRS. Using voltage division principle, Vm is equal to Rm upon Rs plus Rm into V. Taking V on left hand side and remaining term on right hand side, we will get V is equal to Vm into 1 plus Rs by Rm. That is equal to Vm into Rm plus Rs by Rm. Whereas Vm by Rm is Im. And therefore, it is nothing but Im into bracket Rm plus Rs. That is K into Im. Whereas K is equal to Rm plus the series resistance Rs. So therefore, the voltage measured is proportional to the current flowing through the PMMC instrument. When the current flowing through the instrument is Im, there will be deflection on PMMC instrument and the scale is directly calibrated in terms of voltage by multiplying the current reading by the factor K, and directly the voltages are printed on the scale. The RS value can be obtained from the circuit as RS is equal to, what is the voltage drop across RS? That is V minus voltage drop across Rm. That is V minus Im into Rm. That is equal to voltage drop across Rs. And therefore Rs is equal to VRS divided by Im, and therefore it is V minus Im Rm divided by Im. By selecting various values of resistance Rs from Rs1, Rs2, Rs3 up to Rsn, you can have multiple voltage ranges for the DC voltmeter, and that is shown in multi-ranging voltage DC voltmeter. So V1, V2 and V3 are the maximum range values, and those can be K1 into Im, K2 into Im and K3 into Im. Whereas K1, K2 and K3 will be decided by the value of RS1, RS2 and RS3. So appropriate value of RS1 and RS2 and RS3 can be selected so that you can get multi-range voltmeter. A typical multi-range voltmeter with various voltage ranges shown here: 10 volt range, 50 volt range, 100 volt range, 250 volt range and 500 volt range is shown here. Whereas the voltage to be measured is supplied through a range selector switch. Whenever the switch is in 50 volt position, the resistance RS2 is coming in series, and the calculated value of the current Im is flowing through this PMMC instrument, which can give the deflection, full scale deflection at 100 microampere, which is having the internal resistance of 500 ohm. Actually, from the formula of RS, this value of RS1 and RS2 up to RS5 can be calculated for various values of V1, V2, V3 up to V5 as the maximum range value. And that's all about the multi-ranging DC voltmeter. That's all about this unit. A typical examples are shown here, sometime asked in the exam paper. For example, if two ammeters are connected in parallel, say M1 and M2, with the two internal resistances, one meter 1 is having the internal resistance RM1 of 0.01 ohm, and another ammeter is having the internal impedance of 0.05 ohm. Then what will be the total current I flowing through the circuit? The first meter is of 10 ampere scale and second meter is of 15 ampere scale. And what is to be obtained? That when these meters are connected in parallel with two different internal impedances, how much reading meter 1 shows and how much reading meter 2 shows, means how much current meter 1 is sharing and how much current meter 2 is sharing. So we use the current division principle again. I1 is given by the resistance of meter 2 divided by the total resistance into current I. So note here, when you want to find the current through the parallel combination of any number of meters, then you can take the equivalent resistance coming across that meter in the numerator and the total resistance in the denominator and multiply it by the total current. Then it will give you the current which is shared by that particular meter. So here I1 comes out to be 33.34% of I and I2 comes out to be 66.67% of I. And here the I will be decided by the external circuit. For example, it can be the load current. So 15 ampere meter shows the 66% of reading and 10 ampere meter shows 33% of reading. The total will be 66.67 plus 33.34, that is 100%. So total current I will be divided in two parts and each meter is reading the part of the current flowing through it on the dial. Another example, a moving coil instrument gives the full scale deflection of 20 milliampere, means when 20 milliampere current is flowing through the coil, the pointer will be deflected to the maximum value of the reading when the potential difference of 50 millivolt is applied. Okay. Calculate the series resistance required to measure 500 volt on full scale. So this is the question of converting a PMMC instrument to a voltmeter. So what is given to us? The meter full scale deflection current is given, that is 20 milliampere. And the full scale deflection voltage across the meter is given 50 millivolt. Let us see the equivalent configuration of voltmeter. One series resistance is there and the PMMC instrument is there. The resistance Rm of the meter can be easily obtained from the ratio of the voltage drop across the meter divided by current through the PMMC instrument, that is given 50 by 20 milliampere, that is 2.5 ohm. So meter resistance is 2.5 ohm, which is in series with the resistance RSE, that is the series resistance. We want to make this meter to measure the 500 volt. The maximum deflection current is 20 milliampere flowing through this. So this 500 volt is getting divided across RSE and across RM. So across the meter we know the voltage, full scale deflection voltage is coming out to be 50 millivolt. So what is remaining across RSC? That is 500 minus 50 millivolt. So approximately 500 volt, which is coming across the series resistance. So we can calculate the values of series resistance by Ohm's law. Voltage divided by total resistance. Total resistance is RSE plus RM, across which 500 volt is applied, and current flowing through is IM. So therefore IM is 500 divided by RSE plus RM. Here RM is given 2.5 ohm and IM given is 20 milliampere. So take RS on the left hand side. After simplification, you will get the series resistance comes out to be 24,997.5 ohm. That is approximately 25 kilo ohm. So when you connect RSC of 25 kilo ohm with the selected PMMC instrument, then this instrument can be in total used as a voltmeter to measure the voltage from 0 to 500 volt. So similar example problems are asked in the previous examinations are shown here for your reference. Let us see the next device, that is AC instruments. Up till now we have seen the measurement of DC voltage and DC current using PMMC instrument as voltmeter and ammeter. Whereas PMMC instruments can work only with the DC supply. They cannot work with the AC. Because when the current flows in one direction, the force is moving in one direction. When the input changes the direction, the current direction change and force also changes the direction. So pointer will continuously moving up and going down. And since due to inertia, the pointer will never move if the frequency of the input AC current is changing rapidly. And that's why PMMC instrument doesn't work on DC. Then how to solve the problem? Simply to measure the AC quantity, first convert it to DC, and we know the converted DC value is proportional to the AC RMS value, and therefore it can be simply done by connecting a bridge rectifier in series with the input source. And the rectified signal is then connected to PMMC instrument, which reads the DC output of the rectifier, which is proportional to the RMS value of the AC input. The dial of the PMMC instrument is directly calibrated in terms of the conversion factor, that is DC to AC conversion factor, that is average DC value to RMS DC value factor. There is another type of instrument that can be used for measurement of AC quantities. Those are called as moving iron instrument. So we will see the moving iron instrument in the next part of this lecture. So till then, bye bye friends.